Hello everyone, thanks for joining. My name is Selvakumar Panir. I'm a senior graphics software architect at Intel, and I lead a research project that focuses on gaming, generative AI, and graphics research at Intel Labs. And in this talk, Simplified Data Collection for AI on CPU, GPU platform, I'll go over the unified data collection pipeline that we have built that seamlessly simplify the data collection workflow for generating data sets for AI in real-time rendering. Here are some of the primary motivation for this talk. Achieving photorealism in real-time rendering has always been a challenge for decades. It requires significant compute and memory bandwidth. So for several approximation techniques have been used to achieve photorealism in real-time rendering, and several hardware and software acceleration techniques were evolved to solve this problem. And more recently, AI acceleration support in GPU is bringing new ways to render a frame faster and better. But still, there are several pain points to collect data, and there are several limitations from the softwares to collect the data from the GPU. And we can see that today AI has been showing promising impact for content creators, game developers, and all the way to the end users, where it is helping to bring better user experiences. For example, at the content creators level, Intel OpenImage Denoiser is helping to improve the workflow efficiency by rendering the frame with low samples and use AI-based denoising technique to reach the high quality output. From the game developer's point of view, Unity Art Engine uses AI to seamlessly bring real-world captures as textures in games and interactive experiences. And taking it all the way down to the end user experiences, AI is helping end user to get lower latency, high throughput, and high quality in games by using AI techniques. For example, the neural supersampling for real-time rendering from Facebook Reality Lab is helping to render a scene at much lower sample rate and bring much higher quality using AI. They're certainly helping to bring better gaming experience to the end user. Let's look at real-time rendering challenges where AI can help. The first one is how AI can help to address development flow challenges. The diagram shows the differences between 3D artists developers during a game development workflow. For example, in a typical game development workflow, the 3D artist is responsible for developing the 3D models, textures, materials, lighting, animations, and all the assets for the game. And these get transferred to the developer, where the developer takes those assets and then integrate that into a game engine and develop custom shaders, render passes, post filters. And this is an iterative loop between the 3D artist and developer. And the developer is also responsible for making sure that the end game is playable on all the GPU families, for example, on mobile devices, laptops, consoles, desktops, and so on. So there is an iterative process between the developer working with the GPU families to make sure that the end result is playable, as well as to kind of satisfy what the 3D artists intend to see as the final output in the game. So these are the two pain points that can be solved with AI. And for example, how to simplify the differences between 3D artist and developer. And this is one where AI can certainly help, where many of these things that are currently have a dependency on can be eliminated in the future using AI. And for another aspect is how to avoid redundant development work. Many of the things are already there in the 3D modeling softwares, but then we have to recreate them in the rendering engines. And this is another area where we believe that AI is going to address in the future. And the other aspect is how to avoid redundant memory reads and writes in the GPU pipeline. And typically games, when they are bounded, they're bounded by either by compute or memory bandwidth. And this is another area where we believe that AI is going to be impacting in the near future, where AI can learn the texture parameters, so we don't really need to bind the textures in the future, and we can infer during inference, we can actually get the texture values. So with that, we can also even achieve fixed render time, where the AI can learn the complexity of the scene. So today, the complexity of the scene defines how the frame rate would be. So with AI in the near future, we believe that we can attain a fixed render time and have the AI learn the complexity of the scene. And the second challenge is how AI can address rendering challenge in the GPU pipeline. The diagram here shows a combination of fixed function logics and programmable cores to render a primitive. And I have shown here a simple screenshot of a cube rendered on top of a plane. And if you take a pixel from this particular rendering, and then if we can actually go back into the pipeline, we can have access to the triangle that contributes to that pixel. And if we go back again, we can actually even get to the triangle vertices that contributes to the triangle. And we can even go back and see that that pixel is coming from the cube. So this hierarchical information is so powerful for neural networks, and can be completely free to grab from the game engine. So we developed this pipeline to actually gather all this information while a scene is getting rendered. How do we get access to these data from every stage of the pipeline? Starting from the modeling software, for example, at Blender, we have access to generating high quality ray traced output from 3D models, and also access to the intermediate buffers that Blender renders while ray tracing the scene. And we also have access to the complex rendering, and Blender has been around for over 27 years, so they have perfected a lot of things. And for example, fur and caustic dispersion effect, these are something that's very complex to render, can be rendered very easily in Blender. And so we have access to that for generating very high quality outputs. For example, caustic dispersion is an area where we can bring a lot more realism into underwater scenes with real-time caustics. That is now possible with Blender as well. And we have also access to the 3D models, animations, and even all the procedural workflow that Blender offers. And everything can be accessed through Python script. This is another tremendous opportunity for us to use the Python script to collect data from the modeling software. And going down to the game engine, and game engine have access to a little lower level information. For example, through the game engines, we have access to the forward rendering or deferred rendering stages. Like for example, G-buffers can be accessed from the game engines. And the game engine also give access to the GPU pipeline. And for example, for every pixel that gets rendered, we can get access to the primitive that actually is used to rasterize the final pixel. And we also have access to the vertex information that contributes to that primitive. And we also have access to the game engine specific metadata. For example, the way the game developer put together the scene, we have access to the hierarchy of the scene from the game engine. And in certain cases, not all game engines provide access to all the API parameters. For example, DirectX 12 gives access to change the subpixel sample location. This is a tremendous opportunity to collect very subpixel level information from the rendered scene. So typically games can render at 1 sample per pixel, or with MSIA settings set to 2x or 4x, we can render 2 samples or 4 samples per pixel, all the way up to 16 samples per pixel. But at the API with DirectX 12, now we have access to changing the sample location all the way up to 256 samples per pixel. This gives a tremendous opportunity to collect every subpixel color from intercepting at the API runtime level. And we can also add additional render passes that are not possible in game engines at the API level. Going down one level to the driver level, now we have access to the DDI level information or the Intel GPU level information. These are things that are not exposed at the API runtime level, but we still have access to from the driver level. So we can get access to some of the lower level information from the GPU through the driver level intercept. So when it comes to data collection, here are some of the top level questions that many people will come across. One is how to capture a scene at the highest quality settings. Sometimes these are limited by the capabilities of the game engine. And so, like I mentioned in the previous slide, in certain cases, we have access at the API level where we can actually render a frame at the highest quality setting by rendering up to 256 samples per pixel. And in some cases, how to generate a ground truth image beyond the current game engine limitations. For example, like fur and caustic rendering, these are something very trivial to do in a modeling software, but it requires a lot of effort to get that in a game engine. So those are the things that we can actually use Blender to collect the ground truth data that are beyond the game engine's limitations. And then how to capture the low-level GPU pipeline information. These are like hierarchical information that anytime a GPU renders a primitive, we have access to. And this is an area where that, as I mentioned, can be very helpful for neural network to learn the hierarchical aspect of putting together a scene by the GPU. And the last one is how to automate the capture process by changing the camera angle, materials, and lighting conditions so that we can actually collect a lot more data to train the neural network. So let me go into the data collection pipeline that we have built. So if you take a typical flow today, Blender, where the 3D artist develops the 3D model, and now this can be exported as an FBX scene in one of the use cases, and now we can bring that to Unity. And then from Unity, when it goes to the GPU, it either can go to a DirectX 12 API or some other APIs. And what we have done is we have created this unified data collection pipeline where we can actually intercept every stage of this pipeline and extract the data from the rendering. For example, at the Blender, using Python script, we can capture the ground truth image from different camera angles, different lighting conditions, different materials, and different animation sequences. And then the same scene can be exported into Unity. Now we have access to the GPU hierarchical buffers. And these are very crucial information, and these are sometimes can be the input to the neural network itself. And then going down one level, as I mentioned before, at the DirectX 12 layer, now we have access to the subpixel information, where the same scene can be rendered 256 times to get the subpixel level color values for the same frame. So Blender, as we all know, this is a tool that is widely used by 3D artists, and it's been around for over 27 years, and I've improved a lot of rendering techniques and perfected them over years. And recently Intel added the open image denoiser, which basically gives the opportunity to render a scene much faster by using a AI-based denoising technique, where the scene needs to be rendered only at very low sample per pixel, and using an AI-based denoise, we can actually get much higher quality output. And the tool also, the software also supports rasterization ray tracing engines. And more importantly, the Python script allows us to control many aspects of rendering in Blender. And here are some of the examples where at the Python level we have access to. All we need to do is basically import the BPY module, and now we have access to the frame, we have access to the camera. We can also move the camera through the Python script, and we can also generate multiple keyframes where we can move the camera and then capture a scene. And this is just a beginning. We have access to literally all aspects of Blender, where we can control the material properties, animation sequences, and everything that Blender offers through the Python script. Here's a quick video that shows through the workflow of just kind of generating a data set from the ground up. As we open Blender, this is the default scene. Now the video goes through adding a monkey. This is also part of Blender, a default model. We can smoothen it a little bit. And now with the Python script, now we have access to changing the camera to wherever we want to capture the data from. In this one, I'm just circling the camera around the object, but we have control over keeping the camera in a hemisphere with control the number of points that you want to capture the scene, or the entire sphere as well. And we have complete control over the number of points that you want to capture these objects from various locations. And so this gives an idea of like how powerful the Python integration in Blender is for data collection. And here is an example of all the render passes that are now accessible from Blender. For example, the top left is shown is the ray traced output, the color output, but we can also have access to all the intermediate render passes that Blender can now output to an image file. So for every pixel in the color buffer, now we can also get the normal value, the UV value, the vector, the shadow, and also the diffuse and specular contribution, the gloss contribution, both from the direct lighting pass as well as the indirect lighting pass. And so several more information can be captured from the Blender. And all of this is also scriptable as well, so which gives a lot more opportunity to actually collect not only the ray traced output, but also all the intermediate stages that Blender uses to kind of finally achieve the final goal. And this is also configurable based on the render engine that is used. By default, Blender supports the Cycles render engine, but we can also bring other render engines like LuxCore render engine, which gives even additional metadata that can be captured while rendering a scene in Blender. And that's not all. Blender, like I mentioned, can support things that are currently challenging to do at a game engine level. And for example, we can do realistic fur rendering within minutes in Blender, and these can be used for data collection for very specific needs. For example, if the model that we're building is towards the texturing and lighting, these are some of the aspects where we can bring variability of data for data collection. And the scene that you see on the right-hand side, the caustic dispersion effect, is rendered in Blender using the LuxCore open source render engine, which gives you this nice caustic dispersion effect, which takes only a few minutes to actually put together in Blender. And going to the Unity side, Unity's been around for several years, and it's one of the tools that is used for game development, and it supports Intel open image denoise for baking light maps, and it supports rasterization and ray tracing in real time now. And it have access to scene-specific and render-specific information. Scene-specific information, there is a module called image synthesis that gives access to motion vector, optical flow, and some of the object-level information can be extracted from Unity. And then all the way down to the render-specific, for example, like the gbuffer information can be captured from Unity. And what we have done is we have extended that to capture pipeline-level information. For example, we have, for every pixel, now we have access to the pixel triangle and the vertex info for that particular image that got rendered. And here is a closer view of what that looks like. So the left-hand image shows the unique color for each of the sub objects that can be set up in Unity. And on the middle, what I'm showing is the unique color for each of the primitive. And the right-hand side image is showing the interpolated unique vertex color for each of the primitive. So this information gives a hierarchical view of like how a pixel is finally reached its color value and what are the primitives that contributes to that particular pixel color value. And here's a closer view of that same image where we'll start with the rasterized image and going down all the way to the colored image where now we have access to what sub-objects that is by looking at the color. And here is the primitive ID where we assign a unique primitive color for each of the primitives in each of the objects. And here's the interpolated color values that we can actually also capture from Unity now. And going down to the API level, this gives you a lot more access to the subpixel level information that is now possible at the DX12. For example, the picture shows one on the left-hand side is the single sample per pixel image, and on the right-hand side, it shows the 256 sample per pixel image. And as you can see, you can control this in DirectX 12 very easily using this function set sample position, which gives control over where you want to set the sample position within this pixel grid. And so within this pixel grid, about 16 by 16 samples, we can literally change the sample location for every single iteration and capture about 256 frames and then resolve the final pixel color, which gives this nice smooth image on the right-hand side, as you can see on the right-hand side, as well as all the subpixel color that contributes to the final pixel value for each of the pixel that is rendered. So in summary, our unified data collection approach simplifies the data collection process for training neural networks. And the configurable script at the Blender using the Python script and at the Unity using the C# and shaders and custom shaders, and at the API level where we can actually tweak in or kind of configure at the API level provides endless customization. And the scriptable camera path and the material exchange brings the variability to the data set. We can even use a gameplay from an user and use that to collect data set both from the Blender as well as from Unity. And we can also extend this to support additional data collection in the near future. For example, the procedural workflow, which is getting more popular both at Blender and Unity. With the integration of Houdini in Unity, this is even getting more exciting to collect data from the procedural workflow in the near future. With that, imagine the innovation made possible by the data collection, and the possibilities are endless. Thank you.